Okay, so let us continue our proof. Now, I actually got confused with the proof. I misunderstood a step and I got endlessly confused. And I started thinking that there is something wrong with the proof itself, but that's not the case. Actually, everything is alright and we can now conclude. So, if you remember, we have a finite abelian group whose order is p to the power n, where p is a prime and n is a positive integer. Our aim was to show that G is the direct product of a finite number of finite cyclic groups. And in that direction, we have already proved, we have actually found two cyclic groups. One of them is A1, which is of order p to the power n1, and the other one is A2, which has order p to the power n2. Moreover, n1 is greater than or equal to n2, and a1 and a2 are intersecting trivially, so that the order of the product a1 a2 is equal to the product of their orders, and this becomes this. Now, if one continues this pattern, one would continue to get more and more cyclic groups until eventually one runs out of all the elements. So that is why, and that will happen because G is after all a finite group. That is why. So we can write the last part of the proof like this. Continuing like this, we get cyclic groups A1, A2 and so on up to say AK of orders p to the power nk respectively, such that AI intersection, what you see here in the next step, it will appear like this. Another cyclic group A3 will be found, whose intersection with the product of the two previous ones, A1 and A2, is trivial. So in general, the pattern will be like this. AI minus 1 will be trivial for, okay, so what type of i's we will have here? I can take its value because we are mentioning I minus 1 and things start with 1. So the least value of I will be 2. And of course it ends at k, such that this happens. And G is the product of these cyclic groups. Now, because of these relations, any element in G will be expressible as a product of elements coming from these cyclic groups. Of course, that however follows from this equation. But additionally, such a representation will be unique, and that uniqueness is a consequence of these relations. Okay, and we actually, by this point, we have seen so much group theory. Exactly why such a representation of any element of G as a product of elements of these groups will be unique as a result, as a consequence of these relations, that is obvious, almost obvious. Okay, so I leave that to you to understand why the uniqueness is a consequence of these relations. And in fact, the author also writes here, hence, for any element, well, these are not the exact words of Herstein, but I am just writing the same thing in my own words. For any element x in G, there exist unique elements A1 prime in A1, A2 prime in A2, and so on, AK prime in AK, such that X is equal to the product of these elements in that same order. And that is why G is the external direct product, or is isomorphic to the same thing, because internal and external direct products after all are isomorphic to each other of these cyclic groups. And that's where the proof ends. So, G is the external direct product of these cyclic groups. Okay, now next comes a definition. Definition of invariants of a finite abelian group. And the definition, this definition relies on the previous result, namely that any such finite abelian group is expressible in this way. If G is a finite abelian group, and G is this external direct product, where the AIs are cyclic groups with order of AI equal to O. Okay, I forgot one thing. In the definition, I should have mentioned, okay, let me just write it properly. Okay, I forgot to say that the group has to have order which is the power of a prime. It's not just any abelian group, finite abelian group. Let G be an abelian group. Need not mention finite separately if I am writing the order. Abelian group with order of G equal to p to the power n. Well, you keep one thing in mind, that our theorem which comes before this definition is not just about groups of this type of order. That theorem is true for any finite abelian group. However, the main part of the proof we have done only for groups of this type of order. That's because we were able to reduce the general problem to this case because of a previous result. Okay. This definition, however, is being given only for finite abelian groups having this type of order, where P is a prime and n is a positive integer. Now, by the previous theorem, we know that G is expressible as a direct product. Let G be this direct product where each AI is a cyclic group and order of AI is equal to p to the power ni, where n1 is greater than or equal to n2, which in turn is greater than or equal to n3. In this pattern, the exponents go, and the last exponent is nk, and these are all positive. Okay. Otherwise, actually, there is no point. If some ni is 0, no point writing that factor in this product. Whether you write it or not, it does not ultimately matter. If these conditions are true, then these integers are called the invariants of the group G. Then the integers n1, n2 and so on, nk, are called the invariants of G. Okay. Now, just because we are calling these things the invariants of G does not automatically mean that they are the invariants of G. They exist, we already know from the previous result. However, who knows, maybe another set of invariants also exists for some finite abelian group of this type of order. The definition isn't saying anything about uniqueness. However, it turns out that once you have a finite abelian group like this, then its invariants are unique. Only one set of invariants exists. That's why the invariants. That we will prove. And because these numbers are unique, so they are uniquely determined by G. Now, one must also understand that these numbers are only unique. But the cyclic groups that we see in such a representation of G as a direct product themselves are not necessarily unique. Nor are the generators of those cyclic groups unique. Well, this is something we already know, because a cyclic group may have many generators. But before we write that though, let us see one more thing. Suppose that we have a finite abelian group of order p to the power n, and everything else that we have in this definition we have for that G. Okay. So we have the full setup of this definition. Then what can we say about the order of G and the orders of these cyclic groups? Because G is the direct product of these AIs, so the order of G will be the product of their orders, that is this However, we already know their orders, and so by one of the rules of exponents we get this, and hence n is equal to the sum of these n i's, and note that all these n i's are positive. That condition is also there, okay, for us. All these n i's are positive. Hence, the invariants form a partition of n. We have already come across the notion of partitions in that part where we were figuring out the conjugate classes of symmetric groups of degree n. Okay, there if you go back, you will see that there we have the partition function coming up. And in fact, the number of conjugate classes, I think if I am remembering correctly, is the number of partitions of n for the symmetric group Sn. But anyway, this is one property of the invariants of G, that they form a partition of that exponent n in its order p to the power n. And now let us come to the non-uniqueness of these cyclic groups. So once you have these numbers for a group, they are constant. You will have this many numbers and these are the only numbers. However, these groups themselves are not unique. And one example is given here. You consider this group of order 4, where a square and b square are both equal to the identity, and ab is equal to ba. Actually, ab square whole square is also equal to the identity. So it is a group which is abelian, but itself is not cyclic. And well, it's abelian because it has order 4. Any group of order up to 5 is necessarily abelian. Non-abelian groups start only from order 6. And this is a finite abelian group then. And what is its order? 2 square, which is of the form p to the power n. Here p and n are both 2. So it's expressible as a direct product of cyclic groups, in fact in 2 different ways. And one of them is just this. The cyclic group generated by A times the cyclic group generated by B. Okay. But at the same time, it's also the direct product of the cyclic group generated by AB and the cyclic group generated by B. So you can see that here the invariants are what? 2 and 2. Well, hold on. No. Why? Not 2 and 2. The invariants are 1 and 1. Sorry about that. Because this group has order 2, this one also has order 2, and the same is the case with these two also, where here n1 is 1, n2 is also 1, and they form a partition of this exponent 2. Okay, so these are the invariants. The invariants stay the same, but the expression may be more than 1. Okay. Okay. So now, in an attempt to prove that these invariants are actually unique, there are some things, and in that direction we have this definition. Well, in this definition we have an abelian group. This definition has been given not just for finite abelian groups but for any abelian group. Actually, let G be an abelian group and S be any integer. We define the subset Gs to be the set of those elements x in G such that the power x to the power s is equal to identity. Note one thing immediately, that no matter what the integer s is, this set is non-empty because at least E belongs to the set. E to the power s is E, no matter what s is. This is something we already know. Note that E belongs to G of s. However, more is true. Suppose we consider two elements x and y in G of s. You can probably guess where I am going with this. I am going to show that G of s is a subgroup of G. Then x to the power s is E and y to the power s is also E. Since G is abelian from a previous exercise that we have seen long ago, okay, x y to the power s is equal to x to the power s times y to the power s. So that is also ultimately going to be E. Keep in mind that this is possible only because G is abelian. In general, this is not the case. In general, this will be xy times xy times xy, s copies of xy. And one more thing, using one of the rules of exponents, actually there are two steps, but I have written in one step itself. I have interchanged the positions of these two exponents. So xy and x inverse both belong to G of s. Thus, G of S is a subgroup of G. Now we will need these sets G of S, and there is this elementary lemma about these sets. Next, the lemma concerns two isomorphic abelian groups. If G and G prime are two isomorphic abelian groups, again note that although we are discussing finite abelian groups, that is our main aim, but here we are not really considering finiteness, and the lemma also has been stated for general abelian groups, not necessarily finite. So if G and G prime are two isomorphic abelian groups, then for any integer S, GS is isomorphic to G prime S. The statement is very natural. In fact, it's so natural that it seems that there is no need for any proof. But of course, we need to prove it. And when you see the proof, yeah, it is easy, but it's not exactly trivial. It's not something that there is no need to even see. Okay, so let's see the proof. Because these are isomorphic, so there exists an onto isomorphism. So we can assume one. Let phi from G to G prime be an onto isomorphism. And let us again recall that in most of algebra books, isomorphism is by definition onto. However, in Herstein's book, isomorphism by definition is only one-to-one. A one-to-one homomorphism has been defined to be an isomorphism by Herstein. That's why we are separately writing onto. Okay. Now we need to prove that there exists an isomorphism between G of S and G prime S, which is also onto. Consider the restriction. Oh, and there is one more subtle thing which may be overlooked. These two are isomorphic. For that to be meaningful, these themselves have to be groups. And they are, because we have already shown that these are subgroups. Okay. Now consider the restriction of phi to G of S. The second group does not change, of course. We have restricted phi to the subgroup G of S of G. Okay. And we already know that when we restrict a function, it still remains homomorphism, provided of course we are restricting it to a subgroup and not just an arbitrary subset. Okay, so this is a subgroup. So this restriction is also automatically a homomorphism. Moreover, the original phi was one-to-one, so this one is also one-to-one. Clearly, this restriction is, and that means one-to-one homomorphism, so it's an isomorphism. So this is an isomorphism. All we need to show now is that it is onto. Well, I mean, this itself is not onto. That's not what we want. We want to show that the image of this homomorphism is G prime of S, which is a part of G prime. Let's see. Let X be any element in the domain of this restriction, that is G of S. Then x to the power S is equal to E. That's the definition of GS. So what will you get if you take this power of phi of x? Because phi is a homomorphism, you will get this, which is equal to this. And of course, you understand that by E prime we denote the identity element of the group G prime. Okay. And this means what? This means that the S power of the element phi x in G prime is equal to E prime. So phi of x has the requisite properties to be in G prime of S. Hence, phi of x belongs to G prime of S. So the range of phi is a subset of G prime of S. We want to show that actually it's equal to G prime of S. So now we have to prove the reverse inclusion. Or shall I write like this? Oh, see what I have done. I have actually completely gone against my own convention. I mean, of course, it's not my convention. What is that convention? The convention is to write functions to the right of the argument. But of course, you can probably excuse me for this slip up. I mean, I was not really paying attention to that convention. Rather, I was thinking about the proof itself. So ideally, I should have written E phi. Okay. So if you are following everything according to that convention, then this is not how you should write these parts. You should write instead E phi x phi to the power S and so on. Okay. So I will rectify that mistake right now. Here, however, I am not going to do anything. So the range of this restriction, it's I was going to write the range, no, then I noticed that I did this mistake. So now I won't write phi of G of S, but this. This is contained in G prime of S. Now let us consider an element there. Now let y belong to G prime of S. Then y to the power S is equal to E prime. So that is one thing. And the other thing is that y being an element of G prime of S is after all an element of G prime, because G prime of S is a subgroup of G prime. And our original phi is, I mean this one, is onto. Okay. Since y belongs to G prime and phi is onto, there exists x belonging to G such that x phi is equal to y. Well, you may object, why are we not straight away writing that there exists x belonging to G of S? That's because we don't really know whether this itself is onto. No, we do not know that. This is the restriction. We know that this is onto. That's why I can write only this. But of course, now everything will be clear. We can say much more than that. Alright, now if you combine this relation and this relation, then what do you get? So, x phi to the power s is equal to e prime, or because phi is after all a homomorphism, that's why the s goes inside, and e prime we already know is e phi. Alright, what will you do now? Now you use the fact that phi is 1 to 1, it's injective. Since phi is 1 to 1, x to the power s has to be equal to e. And now only because of this we can conclude that x belongs to g of s. So, x belongs to g of s. So, any element in g prime of s, y, appears as the phi image of some x. Okay. However, that x belongs to gs, which means that this y belongs to this image. Thus, y belongs to this. Hence, just like this is a subset of this, this is also a superset of this. Okay, any element here is also here. So, and that is why if we now change this function, this restriction, by changing its range or its codomain, no matter what you want to call it, from g prime to g prime s, then it will still be an isomorphism, because it will not lose its one-to-oneness or homomorphism property, but additionally now it will be onto as well. So it will be an onto isomorphism. Hence, is an onto isomorphism, and an existence of such a function allows us to say that this and this are isomorphic, which is what we wanted to prove. Okay, so that's where the proof ends. After this, of course, there are many more things which we will see in the next upload. So that's just it for tonight, folks. See you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.